Given a matrix that has p rows and q columns, recall that we can represent it as a single column of row vectors. So row 1, row 2, up to row p, where the row vectors consist of the components in the respective row. So for example, row p will have the components AP1, AP2, and so on, up to APQ. And similarly, we can represent the matrix using column vectors. So we have C1, C2, up to CQ. So for example, the column vector CQ has the components being the entries in the last column. So we have A1Q, A2Q, and so on, up to APQ. Now the row space of matrix A is the subspace of the vector space of q tuples spanned by these row vectors. So effectively the span of the set of row vectors from R1 to Rp is equal to the vector subspace R, which is a subspace of Rq. And similarly, the column space is the subspace of Rp that's spanned by the column vectors of A. So in other words, the span of the set of column vectors being C1, C2 up to column Q is equal to C, and C is a subspace of Rp that's spanned by these column vectors. So note that here we have Rq because each row vector has q components, and here we have Rp because each column vector has p components. So think about this. Now the null space of the matrix A is the solution space of the homogeneous system of equations, and the solution space, for example, consists of the solutions x1, x2, and so on. So the solution space of Ax equals 0 is the null space of the matrix A, and the null space is also a subspace of Rq, or the vector space of q tuples. Because remember that each row vector had q components, and therefore each solution vector will have the same number of components. Recall that the matrix product A multiplied by X can be written as a linear combination of the column vectors. So that would be x1 by the column vector 1 with the following components, plus x2 by c2, and so on, up to xq by the column vector in column q. So therefore this linear system can be written as Ax is equal to the linear combination of the column vectors, which is equal to the vector b on the right hand side. Then we say that Ax equals b is consistent if and only if b can be expressed as a linear combination of the column vectors of this matrix A. Or in other words, if the vector b is in the column space of A. So what we would do is solve for x by Gaussian elimination, and then express the vector b as a linear combination of the column vectors to show that it's in the column space of A. Recall that if xp is a particular solution of a consistent linear system, Ax equals b, and S being a set of vectors S1, S2 up to SR is a basis for the null space of A, then every solution of Ax equals b can be written as the particular solution plus a linear combination of the basis vectors for the null space of A. So we have C1 by S1 plus C2 by S2 plus another constant CR by SR. So in other words, the general solution of the consistent linear system can be expressed as a superposition of the particular solution of Ax equals b being the non-homogeneous system, and the general solution of Ax equals 0 being the corresponding homogeneous system. So remember, in a previous example we had this as matrix A and this as vector B, and we solved for this system and obtained the following solution. So we used Gaussian elimination with back substitution to do that. And similarly, we also solved for the homogeneous linear system being Ax equals 0 and obtained the following solution. And if you rewrite this in matrix form, so I have x1, x2, x3, x4 is equal to t being a real parameter multiplied by 0, 4, minus 5 on 2, and 1. So recall that this here is the basis vector for the null space of A. So here we can see that we have 0, 4t, minus 5 on 2t, and t. So therefore the particular solution, xp, is equal to minus 9 on 2, minus 5 on 2, 15 on 4, and 0. So as you can see, we can superimpose xp plus the linear combination of the basis vectors in the homogeneous solution to obtain a general solution for the consistent linear system Ax equals b. We're going to show that elementary row operations do not change the row space and null space of a matrix, but they alter the column space. So given a simple example, if we reduce this to row echelon form by row reduction, we subtract 2 by the first row from the second row. So we have 1, 2, and 0, 0. So now if we want to determine the row space of A, we write some arbitrary vector b with components b1, b2 as a linear combination of the row vectors. So there'll be some constant by 1, 2 plus some other constant by 2, 4. So here we're solving the linear system being C1 plus 2C2 equals B1, and 2C1 plus 4C2 is equal to B2. So we augment the coefficient matrix with the components of the vector B. So in this case, if you subtract 2 by row 1 from the second row, we obtain 0, 0, and B2 minus 2B1. So for this to be consistent, we have B2 minus 2B1 must be equal to 0. Now similarly, we can write an arbitrary vector with components B1, B2 as a linear combination of the row vectors of the reduced matrix. So that'll be 1, 2 plus C2 by 0, 0. So in this case, we have C1 is equal to B1 and 2C1 is equal to B2. So if we multiply the first equation by 2 and subtract the first equation from the second, we can see that B2 minus 2B1 is equal to 0. So effectively, the row vectors in both matrices span the same space. Now if we try this with the column vectors, so we have 1, 2, and 2, 4 being the column vectors of A, you're going to get the same condition. And now using the column vectors of the reduced matrix, we have some vector with components B1, B2 is equal to a scalar by the column vector 1, 0 plus another scalar by the column vector 2, 0. So in this case, we have C1 plus 2C2 is equal to B1, and 0 is equal to B2. So you can see that from this condition, to check for consistency, b2 minus 2b1 is clearly not equal to 0. So therefore the reduced matrix and the matrix A do not have the same column space. And now for the null space, we want to verify that the solution space of AX equals 0 is the same as the solution space of Rx equals 0, being the null space of the matrix A and R. So remember that doing the row reduction, we have 1, 2, 2, 4 augmented with 0 on the right hand side. And here we have 1, 2, 0, 0 augmented with the 0 vector. So this tells us that x1 plus 2x2 is 0. And if you subtract 2 by row 1 from this second row, we get zeros. And this gives us the same result. x1 plus 2x2 is 0. So if we designate x2 as some parameter r, then x1 is minus 2 by r. So therefore we can write the solution as x1, x2 is equal to r by minus 2, 1. So this basis vector spans the solution space, or the null space, of both A and R. So the elementary row operations did not change the null space of the matrix A. If we have a matrix that's already in row echelon form, then the row vectors with leading ones form a basis for the row space of matrix A. So for example, here we have 3 rows with leading ones. So the first row vector is 1, 0, 2, 5, and the second row vector is 0, 1, 2, 1, and the third row vector is 0, 0, 1, and 5 on 2. So these row vectors form a basis for the row space of A. Now alternatively, the column vectors with leading ones of the row vectors form a basis for the column space of the matrix A. So here we have a leading 1 in this row. So the column vector 1, 0, 0, and we have another leading 1 in this row. So we have another column vector 0, 1, 0, and a leading 1 in this row. So we have the third column vector 2, 2, 1. So these 3 column vectors form a basis for the column space of A. As we saw, doing elementary row operations on A alters the column space. So for example, where B is obtained by subtracting 4 by row 1 from row 2, the row space and null space of both matrices is the same as we showed previously, but the column space is no longer the same. So if A and B are row equivalent matrices, then a given set of column vectors of A are linearly independent. So for example, we can write some scalar by the first column vector in A, which is 1, 4, plus another scalar by the second column vector is equal to the 0 vector. So these vectors are linearly independent if and only if the corresponding column vectors of B are linearly independent. So we must have some constant by the first column vector of B, which is 1, 0, plus another scalar by the second column vector of B being equal to 0, only if C1 and 2 is equal to 0. So remember that a basis means that the column vectors are linearly independent, and any vector in the column space can be written as a linear combination of these column vectors. So this set of column vectors 1, 4 and 2, 8 forms a basis for the column space of A if and only if the corresponding column vectors of B, which are 1, 0 and 2, 0, form a basis for the column space of B. So again, any vector in the column space can be expressed as a linear combination of the column vectors in B. And the column vectors of B must also be linearly independent to form a basis for the column space of B. So what these basically tell us is that the elementary row operations do not affect the relationships between the column vectors in both matrices. So in this case, given that column 2 in A is equal to 2 multiplied by the first column in A, then these columns are linearly dependent, and consequently the columns in B are also linearly dependent. So as we can see, column 2 in B is still equal to 2 multiplied by column 1 in B. And we can see that in B we only have one row with a leading 1, and therefore the corresponding column that forms a basis for the column space of B is the column with the vector 1, 0. And correspondingly, if column 1 in B forms a basis for the column space in B, then column 1 in A is the corresponding column that forms a basis for the column space of A. So effectively, we reduce A to row echelon form, and then we can find a basis for the column space of the reduced matrix formed by some of the column vectors in that matrix, and the corresponding column vector in matrix A forms a basis for the column space of A. Suppose we have a set of vectors being v1, v2, up to some vector vr. and we want to find a subset of these vectors that forms a basis for the span of S. And we want to express the vectors not in that basis, so the other vectors, as a linear combination of the basis vectors. So for example, if we have a set of vectors being 0, 1, 2, 1, 0, 2, two, 2, 4, and 1, 5, 2. So what we will do is assemble these into a matrix of column vectors. And if we reduce this matrix to row echelon form by elementary operations, then we obtain this matrix with the column vectors C1, C2, C3, and C4. And we'll look for the rows with leading ones, which occur in columns 1, 2, and 3. So therefore, the corresponding columns 1, 2, and 3 form a basis for the column space of this reduced matrix R. And therefore the corresponding vectors in columns 1, 2, and 3 of this matrix A, which is row equivalent to R, form a basis for the column space of A. Now to write the remaining column that's not in a basis for the column space of A as a linear combination of the other column vectors forming the basis, then it's simpler to do so with the reduced matrix. So what we can write is column 4 having the components 5, 1 and 5 on 2, being equal to some constant by the first column vector plus another constant by the second column vector, and then plus a third constant by the third column vector. So we can see that C3 must be equal to 5 on 2, because we have 0 plus 0 plus 5 on 2 is 5 on 2. And C2 must be equal to minus 4, because we have 5 on 2 by 2, which is 5, minus 4 by 1 plus 0 is equal to 1. And therefore C1 must be 0, because we have 5 on 2 by 2 is 5, plus 0 by 1 is 5. So therefore the column vector in column 4 is equal to 0 by the column vector in column 1, minus 4 by the column vector 2, plus 5 on 2 by the column vector 3. And consequently, for matrix A, we have the column vector 4 is equal to minus 4 by the column vector 2 plus 5 on 2 by the column vector 3. And I'll leave it for you to verify that this is valid for this matrix.